Hello student to the foundation of classical electrodynamics course. So, under module 2 today we have lecture number 30 and we will going to discuss about the electrostatic energy that we started in the last class. So, today we have class number 30. So, we have already discussed that the energy associated with the electrostatic charge when they are being from infinite to some place, the work done is replaced by this form, where phi k is the total potential experienced by the charge qk. Okay. So, this potential, total potential is created by all the other charge except qk. So, that potential going to experience by qk, and that is the form. For two charge particle, for the system of two charge particle staying to point R1 and R2, the charge sitting here say Q1 and Q2, for this system we calculated the potential energy W1 as to be Q1 phi 1 2, and that is equal to Q1 Q2 divided by 4 pi epsilon naught and R2 minus R1. And the half term is not there because we are not taking care of another, because if you make Q2 phi 2 1, then it should be Q2 Q1 and R1 R2, that is the same quantity I am considering twice. So, that is why the half term is not there. So, that is the reason once we calculate for the set of charge particle, the energy of the set of charge particle, that is Q1, this is for a set of charges. Q1, Q2, Q3 and Qn, there are n charges are there. So, and with the position, having the position, they have the corresponding position, say R1, R2, vector R1, vector R2, vector Rn. These are their position. Okay. So, now for that, if we calculate, the expression should be something like this. It should be half, and this half, it ensure that I am not taking account the term twice, but I should not be equal to j for I j divided by 4 pi epsilon 0 and R j minus R I. Another way also it is defined, and that is, if I want to don't want to put this half term, then it should be simply for all pairs. I am adding these things for all pairs, and then it should be Qi Qj divided by 4 pi epsilon 0 and that quantity. And when I write all pairs, so that means I am taking Q1 Q2 as a pair. So, I am calculating this quantity once, not Q2 Q1, but if you calculate Q2 Q1, for example, I can take 1, J can take 2, also I can take 2, J can take 1. So, that means I am calculating these things twice. So, in order to avoid this, that is why I need to make a half here, put a half here, but I can avoid this half by just writing, I will do the same calculation for all pairs. So, that means Q1 Q2 now only behave like a one pair. So, only one calculation will be there, that is Q1 multiplied by Q2 divided by 4 pi epsilon 0 R2 minus R1. It should be the same thing if we just interchange 1 and 2, but in that case I am adding twice, that is why the half term need to be there. So, we will do one problem, then things will be much clearer. Okay. So, now we will going to do one thing, and that is for a continuum with the charge density. So, for a continuous charge distribution, and for that case we have a charge density and that is rho, which is a function of r. Okay. So, what happened if I have a continuous charge? So far we are dealing with discrete. Now, for a continuous charge distribution where we have the charge density rho as a function of r. So, this is the distribution we are having for some coordinate system, and for this charge distribution I want to find out the energy. The energy simply will be half integration of rho 2 r rho 1 r prime divided by 4 pi epsilon 0, and this is r minus r prime, and then dv prime, right. This, so if I compare with the with this equation which is shown here, I just replace everything in terms of the charge density rho. So, then I need to put some integral, volume integral, and this volume integral will give us the corresponding charges. So, there should be two volume integral here. Okay. So, now so I can in principle put another line here to make it two volume integral, one is over V and another is over V prime. Okay. So, now I can find the potential for say phi 1 at r, and that is simply 1 by 4 pi epsilon 0 integration of rho 1, which is placed at r prime point dv prime divided by r minus r prime. So, that we know, because the potential for a charge distribution rho 1 at some point r is simply this. So, this we know. So, I have a charge distribution here, which is at r prime point, and if I want to find out what is the potential at r, sorry, it should be small r, at r, the potential should simply comes out to be in this form. Okay. So, now if that is the case, so I can simply, you know, inside the W, if you look carefully, I already have this term, right. In the W I have rho 1 r prime, then r minus r prime, and then we have dv prime. So, all this term is in principle here. So, I can write this W, I can write this W like this. So, this is half, I can extract out rho 2, which is say at r, and then group all this term that I just wrote here. So, that is r 1 rho r prime, then dv prime divided by 4 pi epsilon 0, then r minus r prime, bracket close, and then for this I already have dv. So, this term I just group, and this term is nothing but phi 1 at the point r. So, my W I can write it as half integration of rho 2 at r 2, sorry, r prime point at r prime point, and then the potential phi 1 at r. And this is over dv. Okay. So, that is typically the form of the W. Now, if we look carefully again, what we have, I can write phi 2, which is say function of r prime, and that potential can also be written in the similar fashion, integration of rho 2 r divided by dv divided by r prime minus r, and that should be the potential at r prime, right, in the similar way, due to the distribution of the charge at some location r. So, that means I can over the volume integral V. So, I can again write my W by taking half integral of rho 1, which is at r prime, and then I just group this term which I just wrote here, rho 2 r dv divided by 4 pi epsilon 0 r prime minus r, bracket close, and then d of v prime. So, this quantity simply comes out to be half of, you know, rho 1 r prime and then phi of 2 r prime dv. So, you can see I already have an expression of W here in terms of rho 2 and phi 1, and again I am having, this is say equation 1 and this is say equation 2. So, from 1 and 2 I can write an expression like this. So, from 1 and 2 from 1 and 2 what we get? We simply get integration of rho 2 r and phi 1 r dV is simply equal to rho 1 r prime phi 2 r prime dV prime. So, this is a identity, and this identity is called the Green's reciprocity. This is a theorem, and this theorem is called the Green's reciprocity. Theorem. So, what it says, let me write it down and then briefly explain. So, from the expression we can see that I can have two charge distribution, and for two charge distribution, so suppose I have a charge distribution here and say another charge distribution here. I am just drawing two different symbol to make sure that two different kind of charge distribution you can realize. So, for this case I have, this is the distribution is rho say rho 1 and potential is phi 1, and for this case the distribution is rho 2 and potential is phi 2. So, these are two two different system, but here from the Green's reciprocity theorem you can see that at some point r, whatever the density you are, for example here whatever the charge density you are having, that multiplication the potential due to the charge distribution of the rho 1 at that particular point, if I multiply it and integrate it over the volume, the value is exactly same. If I do the opposite, that means if I calculate the at some point r prime, if I calculate the potential due to the charge distribution of the rho 2 and then multiply the potential and multiply the charge density at that point and integrate. So, these are two isolated system, two different system, but they are related to each other with this theorem, which suggests that I mean whatever the value you find here with just multiplication of rho 2 and phi 1 with the integration of the volume, making a volume integral, you will going to get the same thing if you do the opposite way. So, let me write it down, then things may be clear. So, what I say is this. So, potential energy of rho 2 say at point r in the field produced by rho 1, which is at some point prime, is equal to the potential energy of rho 1 at point r prime in the field produced by rho 2. Which is at r. So, the statement is straightforward that whatever the potential energy we have, so because of the charge distribution of rho 1 and rho 2, the potential energy of created by the charge distribution rho 1, energy of the potential energy of rho 2, the potential energy of the rho 2 in the field produced by the rho 1. So, rho 1, because of the presence of rho 1, if I have a because of the presence of the charge distribution rho 1, I have a field, and on this field if I put rho 2, then this rho 2 will going to have some potential energy. So, that value is equal to the same thing in opposite way. That means, the same value is when rho 2 produced the potential energy and rho 1 is experiencing that energy. Rho 2 is producing the field and rho 1 is experiencing that potential energy. So, that is the meaning of this Green's reciprocity theorem. In other branches also we have these kinds of reciprocity theorem. This is one of the example we have in electrostatic where this theorem is valid. Well, we can make use of this theorem in certain problems. One just typical problem I like to, which is difficult to calculate in other way, but very simple when we use this this Green's reciprocity theorem. So, so suppose I want to find out the force between two non-overlapping force between the two non-overlapping spherically symmetric charge distribution with total charge Q1 and Q2. So, so electrostatic potential if you calculate, then from that you can also calculate the force. So, our strategy is to find out the electrostatic potential that is created due to this system. So, the system, that means if I have a spherically symmetric charge distribution and they are not overlapping. So, I have two spherically symmetric charge distribution, obviously their radius is different. So, suppose the charge distribution here is rho 1 and that should be say function of r. So, that means from here to here whenever you have some r value you will have a charge distribution that is rho 1 that is defined. In the similar way I have a charge distribution here which I say rho 2 and say from here to here this is say coordinate is r prime. So, if I go from here to here at r prime point I should have a distribution and this is you can see this is a function of r, this is not constant, this is a function of r and suppose the distance between these two is r. So, obviously r is greater than the summation of the radius of these two, that is why they are not overlapping and the total charge q is here q 1 and the total charge is this is mentioned, this is total charge, this is my total charge. And this is total charge. Okay. So, now the electrostatic potential, let us now check one by one what I can get from this. So, the electrostatic potential everywhere outside the distribution rho 2 r prime So, I want to find out the distribution at. So, that thing is simple like. So, I have a charge distribution here, this is rho 2 r prime, but if I want to find out a point here what is the potential, then this potential phi 2 that is simply the total charge divided by, here the total charge is q 2 because q 2 is given, divided by 4 pi epsilon 0 and then the point here to here which is r prime. So, that means as if the total charge is confined to the center and this point charge is confined to the center here, and from here to here this is r, and we know from the Gauss's law that if I have a charge distribution and if I want to find out the field outside this charge distribution, then the field or the potential can be simply like whatever the charge distribution we have and consider the charge due to that charge distribution at that origin point and then just simply calculate that. So, I am just trying to do that. So, this quantity is equivalent to phi, I should write another quantity phi point. So, phi point means as if I compress all the charge to this point and then calculate the potential, which is the same thing. Okay. Now, this is considering all the total charge is replaced by a point charge at the center as I mentioned. So, that is the potential. So, both the cases you will get the same result. Now, the potential energy of rho at some point r, this is the potential energy that rho 1 should experience in the field produced by the charge distribution rho 2 the potential energy of rho 1 in the field that produced by the charge energy produced by the charge distribution rho 2 can be simply written as V E is equal to rho 1 r and then phi 2 produced by rho 2 at point r and dV, right. Now, according to the reciprocity theorem, these can be simply represented by this, that rho produced by phi 2. So, phi 2 is created, phi 2 if I write. So, this is rho, this is rho 2 and then that is at r, and the potential, that potential is phi potential and r dV, right. So, no, I am just simply writing. So, okay, this is not, I am just simply writing the same thing. Phi 2 I just replace by this phi point. So, this has to be not rho 2, this has to be simply 1. So, this is the same thing, because that quantity is simply replaced by this, which I already mentioned here. Now, I am going to use the reciprocity theorem for this equation, and that is here in a different color I am writing. So, this is over volume, this is over volume. So, if I use the reciprocity theorem for this, so now the point charge density will experience the same thing due to rho 1. So, I am writing this rho 1 and dV. Okay. So, the potential, this is for, sorry, this is not potential, this is point. This is point. So, this point potential I can replace in terms of the rho, which is the charge distribution of point charge q2. So, rho p is r is simply the point, this is the charge density for the point charge q2. Try to understand once again that I can make this q2 here distributed having the distribution, the charge density like this. This is equivalent to, I can make this point charge q2 sitting here, this charge distribution, entire charge q2 to make a point charge here with the density of this point charge to be rho p. This is the point charge density for this point charge. rho p. So, now rho p, what is rho p? Point charge density. This is we know from the delta function definition, this is q2 delta function r minus r, okay, because now q2 is here, q2 is sitting here. So, which is in r. So, when I shrink everything to the point, well, then my VE simply q2 integration of, because this is here, I rho p just replaced by q2 delta function, then it should be delta function r minus r, and then phi 1, then r, and then dV. So, this quantity is q2 and this integration is with the delta function. So, simply I can have this value as whatever the phi 1 at r. So, this quantity simply comes out to be q2 and the potential due to the distribution of the rho 1, and that is also having a charge q1. So, it is q1 divided by 4 pi epsilon 0 and r. Note it, that quantity is total charge q1 divided by 4 pi epsilon 0 and r, that is the distribution, the potential due to the charge distribution here, whatever we have. Okay. So, that is the, today I do not have much time to discuss. So, with that note I like to conclude, and in the next class I will start again the discussion on the electrostatic energy and try to calculate few distribution, discrete charge and some continuous charge distribution, and try to find out mathematically what should be the potential energy for that specific charge distribution or that for specific distribution. So, few problem I would like to solve in the next class. So, thank you very much for your attention. So, see you in the next class.